Okay, what I want to do now is I want to look at EEGLAB and MATLAB. And so what we're going to do is we're going to take one of the data files from the study, which can be found in the new shared Dropbox. You should by now have gotten an email inviting you to share the Dropbox. I realize we've had a couple people who've added late, and I'll need to add them to that email. So we'll do that. But basically, you notice here in my current MATLAB folder, I have installed the EEGLAB 14.0.0b, and you can see the M file is right here. So if I just type into the command window EEGLAB, basically it's going to activate the program, and you should see a GUI open soon. While we're doing that, let's look at my file list here. See if I can remember what I called that file. Let me go back to downloads, because the file list I'm looking for is in downloads. And I think let me check real quick under my recent downloads and see what that file name was. AVP6C part1.raw. So the study had a part 1 and a part 2. Part 2 is just a repetition of part 1. So all we will work with this semester is part 1. So I need to just come over here then and find AVP part 1. Here we go. So I actually have a couple of files here, and we'll go ahead and open 6C. So we always would name our studies for taking raw data. This comes directly from the EEG machine with very minimal processing. There is a little bit of a built-in script that does some very basic filtering, but outside of that, there's very little processing done. So if you lose your GUI, you can come to the MATLAB window and take it back to EEGLAB. It'll bring the user interface back up. And so now what I'm going to tell it to do is I'm going to tell it to import data. And actually, where is, okay, so using EEGLAB functions and plugins, what we're loading is we're loading a NetStation binary simple file. So once again, you have EEGLAB up, you go to File, you go to Import Data using EEGLAB functions and plugins, and we're going to use the NetStation binary simple file. So I'm going to load that. And what is it doing here? Let's try this again. Okay, we're going to import data, use EEGLAB. Sorry, my computer's kind of frozen here. There we go. Find NetStation binary simple file. Okay, now it's going to bring up a directory. Here's my file. Double click that. Okay, now once I do this, it's going to read the headers. The headers are going to tell it things like what was the sampling rate, what are the channels, what's the configuration, etc. It keeps, since this is a plugin that runs within EEGLAB, it sort of keeps a record of where the sensors are located. So I'm not sure what it's doing here. Looks like it's trying to do some weird stuff. Usually it's a pretty straightforward process. We'll let it keep going, see what it does. So I will say that different versions of MATLAB and different versions of EEGLAB perform in different ways. So it's important that once you start, you finish with the same EEGLAB scripts and procedures. and the same person does it. Okay, now it's telling me it's going to import a default electrode location file. This might not correspond to your montage, as EGI has different versions of CAPS. Check your montage in the channel editor and import the correct location file if necessary. We actually do have a channel location file, but we're just going to keep with the one that is the default because in the past it has not been a problem. Now remember, I am running version 14. So if I were you, when I download EEGLAB, I would download um, the same file. Now you'll note too that it says this function assumes you have a 64 channel system version 2, and that's pretty close to what this data we're taking on. Now it's going to ask us if we want to name the new data set. I'll name it class demo 1. When you name yours, you should be sure that you name it with something that identifies what the original is similar to what the original raw data file was. I'm just calling this class demo 1. All right, we'll tell it OK. And then as we went over on the lecture in class, you notice here it now has a data set loaded called class demo 1. We'll go to plot. We'll ask it to plot the channel data. And you can see that it kind of looks like a mess. We're clearly picking up some kind of noise. This is probably 60 hertz. We've got a lot of odd spacing between the channels. This is like an oscilloscope adjustment. It adjusts the vertical sensitivity of the channels. But you will notice, and this steps through time and seconds. So you will notice what we have here does kind of seem like a mess. You'll also notice we have a lot of movement of sort of the background DC. I'm going to continue to play with the sensitivity here so we can be sure we try to get all channels on the same screen. Okay, and you can see now it's becoming obvious. We've got some baseline drift going on here. And so that's not an uncommon thing to see. You can see down here that you've also got some drift. CZ is our reference electrode in this particular configuration. So there are 64 channels plus CZ, which is the reference. The last 4 channels, 61 through 64, are taken on the face and are helpful in removing eye movement artifacts. So really, as far as brainwave signal, you have 60 unique channels. All right, so this looks awful. So what we're going to do first is we're going to come in. Oh, and you can see here's information about our data set. It tells you the sample rate, epoch start, and epoch end. So often in EEG data, you're interested in looking at a particular condition, and you may have that condition repeated more than once. It tells us, yes, we have channel locations. It tells us the size of the file. It tells us the number of channels. Frames per epoch, that just means if you take the sampling rate and you multiply by the number of seconds, that's just the number of samples. So let's go to Tools, and let's filter the data, and let's use a basic FIR filter. And we will filter from 0.5 to 50 hertz. So, okay. And it's going to do some, it takes it a little while to design the filter on the low frequency end, because to cut off from 0 to 0.5, that's a pretty sharp cutoff. So it's a high order filter, and it's having to calculate the digital filter components. So that's what the system is doing right now while we wait. It's much longer on the low frequency end than on the high frequency end. So we're just going to hang on. All right, here is a shape of what our filter looks like. The horizontal axis is frequency. Vertical axis is dB. You can see from 0.5 to 50, we're at 0 dB, which is a gain of 1. And then we cut off very rapidly at 50 hertz. And then the reason you see these funky things is That's just an artifact of the way MATLAB does filter. So we'll give this a different name. We'll call this class demo filtered. And for now, I won't save it as a file, but when you go through doing this, you should select save as a file, and you should enter a similar title so that you really should save as a file in each step of the process, so that if you ever have to go back, you don't have to start completely over. Tell it OK. And now when I come and look at data sets, you can see that I now have data set 2. It's the one that's active. So as I use the commands in this GUI, they're going to operate on whichever data set is currently selected. So let's plot this one. And now you can see a much different appearance of the data. I'll pull this old one up that we did. And you can see there's actually quite a bit of difference. That high frequency noise is gone. If I play with this a little bit, I can kind of deal with the change in the magnitude of these artifacts. You can see more clear separation on the lines. You can change this display, and you can change the settings. So I can change the number of channels I want to display at a time. Let's pick 30. That'll give us a little more ability to see what's going on here. You have a slider here, so you're seeing 30 at a time, but you still have all 64. So you see that, let me go ahead and play with the sensitivity a little bit so that I can increase the magnitude of the EEG part of the signal. All right, so you see now we have some places where we have this odd shape. When you see that kind of shape, that's usually an eye movement. This kind of shape is often a muscle movement. They sneeze, they blink. I think I went too far. A sneeze, a blink, clench of the teeth, squint the eyes, something, it gives you a little bit higher frequency, a little more localized. This tends to be looking from left to right, sometimes up and down, sometimes a combination of the two. These areas right in here, this is the EEG signal. So it's kind of a randomized signal, has quite a bit of different frequency content, appears to be completely random. Okay, and you can see these eye blinks, they show up quite a lot. So what we want to do next is we want to look at a way to get rid of some of these artifacts. So the first thing you can do is you can come in and you can kind of page through your data or sort through your data, and you can select it on the screen. And I'm sorry, my computer is going super slow because I am also recording, and so it's using up a lot of the RAM, and it's not even wanting to clear the screen. So hopefully I can get this clear. But I do have the ability on the screen to make a selection. And I can select that entire kind of bad area, and I can tell it to reject. And it looks like my computer, here we go. Okay, so what do you want to name the new data set? I'm just going to keep it the same. You notice now it shows up with 2 of them. Data set 3 should be exactly the same as data set 1, except it will have that little bad area removed. All right, I'm sorry, same as data set 2, which is filtered. Let's go back to data set 2 and let's look pre-removal once again at that plot. And so let's go to figure 3. Nope, that's not it. Well, let's just plot it again. So once again, I apologize. This is moving much slower than usual because I am recording. So I went in, I selected this piece of data, I removed it, You can page through and it will be very obvious, even if you don't know what you're looking at, it will be very obvious. There are some sections where things just go completely haywire. What you don't want to do is areas like this one on these bottom 5 channels where you see this kind of thing. Just leave that alone for now. We'll deal with that later. The algorithm that we run will deal with that very well. The goal of coming in and selecting the really bad areas, and there are ways to automate this, and there are even ways to automate it within EEGLAB. But it is important to me that you go through this by hand, because I think as you go through by hand, it'll make it easier for you to begin to get a feeling for what these data look like. So that was actually the only one so far that I've seen. All of these, you see how this kind of thing is, it's pretty predictable shape. It's repeated across multiple channels. Our independent component analysis algorithm to delete artifacts is going to do a pretty good job in getting rid of those. So I'm not seeing any horrible, okay, here's another one. So you can see this region kind of right here, say here to here. That's pretty bad. So that one I could live with throwing away. Now, the only problem is we're going to want to try to collect data of similar type. So I've shown you how to throw away artifacts, but I don't want you to do that just yet because I want us to kind of continue on and talk a little bit more about this experiment. So you can see in subject number 6, which is what this data was, you can see that so far we found spread across all the channels maybe 2 places where we have some really bad data. Even this is not too bad. Those are eye movements. You don't see a lot of, huge amplitude swings or anything like that. So overall, this data is pretty clean. I can tell you that subject 1, the data do not look nearly this pretty. Okay, now what we're going to do is we're going to run an algorithm, and at the moment, I'm not going to throw away any of the artifacts. I'm going to run an algorithm here, and what it's going to do is it's going to use an independent component analysis to look for the independent components present in this signal. And rather than talk a lot about that, I'm going to start the algorithm and then I'm going to shut off the recording because this is going to take a while. Anytime you run this on your full raw data set, it's going to take a while. I mean, it's been filtered, but still we haven't really done anything to it except filter it. It's going to take a while because this is a big data set, and the algorithm is it's like you get a starting point, an initial condition, and then it's iterative. And so part of how many iterations it has to make depends a little bit on the randomized initial condition setting. So what you're going to do now in order to run independent component analysis, and the goal here is to try to remove these eye movement and eye blink artifacts. So we're going to go to Tools, and we're going to come to Run ECE and select that. And then you can let it default to everything. So we're just going to let it default and tell it OK. And now it's going to start its iterative process. And it's a training algorithm. It does give me the opportunity to interrupt. I'm actually not going to do that, but I am going to stop the video. I'm going to let this run, and then I'll rejoin you with another video after it's complete.